All right, let's look at some polar graphing basics. Here are our 4 conversions that we want to try to commit to memory. Problem 1. We're asked to graph the point 2, 2 on a coordinate plane. Okay. We know we're in the first quadrant, 2, 2, and here we are. It just gives us a point of reference. We want to convert this point to a polar coordinate and graph the polar coordinate on a different set of axes. All right, so that requires that we use our conversion formulas. So we're converting to r and theta from x and y. Okay. So as seen from above, the radius is going to be the square root of the sum of the squares of the coordinates of the rectangular point. All right, and summing that, we're going to get square root of 8, and when we simplify, we're going to get 2 radical 2. That makes sense when you look at the graph here. If you were to draw in this hypotenuse, okay, we can see that the legs are 2, 2, so it's a 45, 45 right, so the hypotenuse should be 2 square root of 2. As a matter of fact, while we're over here, think about this angle right here. It's 45, it's pi over 4. So using the other conversion formula, okay, inverse tan, arctan of y divided by x. Okay, no calculator necessary. Arctan of 1. What angle has a tangent ratio of 1? Well, when x and y are the same, or y and x are the same, so pi over 4. All right, to complete the requested information, graph the polar coordinate on a different set of axes. So this is your rectangular plane, and this is our polar graph. All right, if I'm going to graph this point, 2 square root of 2, comma pi over 4, where this is r and this is theta. Okay, to graph, we did something backwards in the polar realm. We graphed the angle first, so from center position, we would figure out where pi over 4 was. Well, it's going to be right here. Okay, and then off of that ray, if we have a positive radius, okay, we would go onto the ray, 2 square root of 2, so we're going to say that our point is here. It should match up with where our point is in the rectangular plane. This just provided practice of using the conversion formulas. Okay. For problem 2, convert this polar equation to a rectangular equation. So that means I want to get rid of r and theta, and I want an equation with x's and y's. Okay, thinking about the conversion formulas that are up above. Okay, this is the equation we're working with. Okay, and it closely looks like y equals r sine of theta. Okay, so something we can do here is we can isolate the sine of theta. So y over r equals sine theta. And then I'm going to substitute that in over here. I'm sure there's several ways that you can manipulate this and solve it. There's just one way that I saw. So I have the 9, and then I'm going to multiply that by y over r. Okay, I still need to get rid of r. I've got the y. That's good. So I might do cross multiply. So I'm going to get r squared equals 9y. And when I look back at the conversion formulas, I know that r squared is equal to x squared plus y squared. All right, so at this point, I'm just going to stop and say, you know what, this is a rectangular equation. It doesn't have any r's or thetas. It has x's and y's. We're good to go. Okay, problem 3. Okay, we're supposed to show that this polar equation can be written in a specific rectangular form. So again, it's just manipulation using the given formulas that are above on the top of the note card and just doing some substitutions, etc. Okay, when I'm looking at this equation right here and trying to get a plan together is about how I'm going to make it look like this equation right here. I want to get rid of fractions, so I'm going to cross multiply. Hoping that that's not going to make it more complicated. Sometimes you just have to find an entry point into the problem and hope that you can kind of see where it would need to go to get what you need. Okay, so I have this right here. Okay, then I notice that I can distribute the r squared. Okay, notice I have the 1 that's necessary over here, and so when I study each of these terms, I can rewrite them as squares, and that's going to be helpful. Because inside of here, this is x, and I'm still going to square it, minus, inside of here is y. I'm going to square it, resulting in what I needed. All right, problem 4. All right, so we have a curve drawn in the xy plane, and its equation is given by this polar equation. We want to observe any restricted interval, and we do have one. Theta can only be between 0 and pi. All right, now we're asked to find the angle that corresponds to the point on the curve with x-coordinate -2. Okay, so where's the x-coordinate -2 and find theta? All right, if I'm dealing with the x-coordinate, then I'm thinking about one of the formulas up above at the top of the card, the note card. And if we're talking about the x-coordinate, I think I'm going to need this equation right here. And then what we're going to do is we're going to take the r equation and substitute it in here. Okay, and the additional information is that I'm looking for the angle that has an x-coordinate of -2. All right, would it be helpful to distribute? Maybe, maybe not, but this is a calculator question. Okay, and so for us to find the angle theta, all we're going to have to do is type this into y1, just the way you see it. Okay, graph y equals -2, that horizontal line at -2, and find the intersection on the restricted interval from 0 to pi. So this is a calculator question. Right, the intersection of these two equations right here results in theta. Okay, so again, reminding you guys that theta doesn't go into the calculator, it's x. So this would just be x plus sine 2x quantity times cosine of x. As an alternate method of finding this theta, this angle right here, you could solve one side for 0. You could pull the -2 over and just do an intersection with that equation with the x-axis by finding the root or the 0. All right. Okay, if you turned and you looked at the next note card number 23, it says special polar graphs. And at the top it says you need to memorize the following special polar graphs. In my experience with this test, I've never seen them ask for you to have to memorize and produce one of these graphs. However, I think it's important that you know what they look like, okay, and that you're familiar with them. So my recommendation on note card 23 is to put your calculator in a polar mode and graph each of those, okay, just to observe what the graph looks like. Okay, some of them produce circles, roses, things like that. So I would encourage you on note card number 23 to do that. Okay. We're going to look at two note cards. We're going to look at note card 24, slopes of polar curves, and then area of polar regions. So we're going to turn to note card 24. So it may be helpful at the top of this note card to go ahead and put those I know, two equations, x equals r cosine theta, x equals, it's particular about where I write on this after it's been converted to a Word document, so we'll try over here. Anyway, I think you get the point. I think it'd be helpful to put these two equations. All right, example 1. Okay, you can see there's a ton of space for example 1 because it requires a lot of work. All right, we're going to find points, r theta points, okay, where the horizontal and vertical tangent lines occur, okay, for r equals sine theta, okay, for theta between 0 and pi. Okay, a picture of what we're looking for is this. R equals sine theta is actually a circle that's symmetric with the positive y-axis okay, with a diameter of 1. This coefficient tells us the diameter. Okay, sine is associated with y. It's a positive sign, not negative 1 sine theta. So the symmetry occurs along the positive y-axis. All right, let's look for horizontal tangents. Well, it's clear that we have two horizontal tangents, one up here and one down here. We also have two vertical tangents. So sometimes it's good to know what you're finding, and it can direct your math in case you kind of fall off. All right, let's find the horizontal tangents first. Well, if you look at the top of the note card, it tells us that the horizontal tangents occur when the derivative of y with respect to theta is 0. Because when you look at the slope, you can see that the slope is a combination of y prime over x prime. So for horizontal tangents, we want the value of the slope to be 0, and that requires the numerator to be 0. So I'm just saying here that this work is associated with my finding horizontal tangents. Okay, so we have to find the derivative of y with respect to theta. Okay, so here's our derivative operator. I need to find the derivative of y. Okay, so let's build an equation for y in terms of theta. Well, back up there at the top of the note card was where I was saying, you know what, this is going to be helpful. Y is r sine theta. Okay, well, what's r? Well, it was our given polar equation, so r is tied back up here to this. So our r is sine theta, but we multiply it by sine theta. All right, this is what we're differentiating with respect to theta. So you could do product rule on this for differentiation, or you can see this as sine squared and do the chain rule. So I think that's what I'm going to do here. Rewrite it as a power. Okay, the square either on the inside or the outside. And I'm ready to differentiate. So 2 times sine of theta times the derivative of the inside, which is cosine of theta. Okay, and we're trying to find where this is equal to 0. All right, with a calculator, this goes into y1, intersect it with the x-axis, find the x-intercept. However, this would be something we could do without a calculator. Okay, hoping to remind you that this right here is also equal to sine of 2 theta. That was a double angle identity. And that's one that we really should kind of have close in our memory. Sine of 2 theta is equal to this right here. All right, how do we solve this? This is 0. Sorry, that's 0. That little thing in there shouldn't be there. Okay, how do we solve this for theta? Well, we want to arc sine both sides. So arc sine 0 undoes this sign, and we get 2 theta. All right, then we want to think about the y-coordinates having a, think about the angles having a y-coordinate of 0. So along the unit circle, I can start with 0. Anytime I'm on the x-axis, my y-coordinate is 0. So 0 pi, 2 pi, etc. And remember, tying back to the interval we're trying to solve on, okay, I know clearly that 2 pi is outside of this interval, but we also have to be aware that this is equal to 2 theta. So dividing everything by 2 to isolate theta, all of these, I'm going to trade sides. Okay, theta could be 0 still, pi over 2. Okay, 2 pi divided by 2 is pi, but anything beyond that is outside of our interval that we're given. So these are the only angles that we really want to test or use to find the points, okay, where we have these horizontal tangent lines. All right, so now we're ready to give the polar points. These are just the angles. We need the r values. Okay, so now we're going to tie back to our given polar equation. All right, taking each of these 3 thetas right here, we're going to insert them in for the equation right here and see what results as far as our radius. So I'm going to evaluate the polar equation at 0. So sine of 0 is just 0. Okay, as a result from this, we saw that the angle, okay, so this is our polar point. This is r, this is theta. Our angle that we put in was 0, and our radius was also 0. So think about that point right there. Even though it's in polar form, it is also equal to the rectangular equation. our point. So if you think about it, 0, 0 up here, yeah, we have a horizontal tangent there. All right, so now let's plug in pi over 2. So plugging in pi over 2 for theta, the sine of pi over 2, well, that's just 1. So let's think about what this results in. Okay, so the point here was 1 pi over 2. This is r, this is theta. So look back up at the picture there, and you can see that in polar form on that circle, let me get back up there. Okay, if I'm going to plot this point pi over 2, I go to pi over 2 first, and then I count off of that ray 1 whole unit. So I am up here, and we do have a horizontal tangent. So everything kind of seems to be working out all right. Okay, and just real quick, just to save space, if I were to insert pi for theta, the sine of pi is 0. Okay, so another point that I would get if I evaluated at pi, okay, would be sine of pi is 0. I would have 0 pi. That's another polar point. Okay, think about sketching pi. So pi puts you on the negative x-axis. However, since the radius is 0, you're not moving off any. So this is actually an equivalent point to 0, 0, the origin. So we've found actually two polar points where we have horizontal tangents, and that matches up with our diagram. Okay, so that's horizontal tangents. Okay, now to finish this, we have to find the vertical tangents. Okay, and as described up earlier, that's where the denominator is going to be 0. Dx d theta will be 0. Okay, so following the same procedure, we're going to differentiate x with respect to theta, but we need to get x in terms of theta. Okay, so that requires us to know that x is equal to r cosine of theta. Okay, but our polar equation is sine of theta times cosine of theta. So just replacing r with sine theta. All right, we're going to have to differentiate using the product rule. Just rewriting it down here. Okay, once we do the product rule and we clean it up, we end up with cosine squared theta minus sine squared theta. And we want to set that derivative equal to 0. All right, in solving this without a calculator, I suppose we could move over this term, square root both sides, and so what it ends up being is we're trying to find where cosine is equal to sine. And you can move this term over, square root both sides, you're going to end up with where is cosine equal to sine. And that's going to occur where your x and y coordinates are the same. Okay. Additionally, when you do perform those algebraic steps, when you do move this term over and extract the roots, we also need to consider where they have opposite signs as well because of the squares that are on here. We have to consider those cases. So just looking at my room situation here, I have lack of it. Okay, where are the x and y coordinates the same, or where are they opposites between 0 and pi? And that's going to occur at the angles pi over 4 and 3 pi over 4. Okay, and now to proceed, we would do what we did back up here to find the horizontal tangents. You're going to insert both pi over 4 and 3 pi over 4 into our given polar equation and find the radius values. And what's going to end up happening is, and I encourage you to finish, you might have more room than me, is that you should find the two polar points, okay, where we have vertical tangents on our polar equation. And that's going to be on the left and the right-hand side of that circle. Okay, trying to get back up there. Okay, so we should have two polar points where we have vertical tangents. And just to record them here and what I got, okay, for this point right here, our polar point was square root of 2 over 2, comma, pi over 4. And over here, we had square root of 2 over 2, 3 pi over 4. Okay, and if you think about these polar points at pi over 4, I would be drawing, okay, from here, the origin up through this point, and that does look like a 45-degree angle. Okay. Also, I would be drawing up through the origin through this point, and that does appear to be 3 pi over 4. So the picture should support the polar points that we got. All right, in the next video, we're just going to have to do problem 2 because it is quite lengthy too. So in the next video, we'll do problem 2 on this page, and then we'll do note card 25.